Hey, stats folks. So today we're starting a new chapter, chapter 5, which is going to focus on normal distributions. If you recall last chapter, we worked on probability distributions, and we're going to be finding lots of probabilities using what's called normal distributions. But I want you to think back to something that we talked about at the beginning of chapter 4, and that's the difference between a discrete random variable and a continuous random variable. Remember, discrete random variables can take on just a certain number of possible values. They're countable. Okay? So we might say, okay, if I roll a dice, or let's say I roll a die, okay, what are my possible outcomes? Well, they're just 1, 2, 3, 4, 5, and 6. And we can make a probability distribution for that. And if I graph that probability distribution, it's like a histogram, isn't it? Okay. And in this case, it would be uniform. Okay. And then in a discrete probability distribution, I can say, hey, what's the probability you get a 3? What's the probability you get an even number? What's the probability you get a number 2 to 4 inclusive? Things like that. Okay, easy to work with those probabilities. Now let's remind ourselves on what a continuous random variable is. A continuous random variable can take on an infinite number of values that aren't quite as easily defined. Oftentimes, this is when something's being measured, maybe like a time or a weight, something like that. So let's say that I have a group of athletes, and I was going to record how long it takes them to run the 40-yard dash. That's a continuous random variable because there are no way for us to really list the possible outcomes, right? Somebody might be able to run the 40-yard dash in 4.9 seconds. Somebody might be able to run it in 4.900236 seconds, right? I can't easily draw the possibilities out in a probability histogram like we did over here with the discrete. There's no way for me to do it. Would it make sense for me to say, hey, what's the probability that somebody runs the 40-yard dash in exactly 4.85 seconds? No, I can't ask that. Okay, because somebody could run it in 4.85 seconds, somebody could write it in 4.849763 seconds, right? Part of it is just how close or how good your measuring tool is. Okay? It's a continuous random variable, and our histogram is not going to work quite so well like it is here. Here I can say, what's the probability you roll a 3? Well, we can figure that out because the options only are 1, 2, 3, 4, 5, and 6. It's not, I can't roll a 3 or a 3.02 or a 2.9876, right? It's 3. And if it's not 3, maybe it's 4 or 5 or 6 or 1 and 2. Okay, so that's discrete. Continuous random variables, we aren't going to look at a specific outcome, but we're going to look at ranges of outcomes and talk about their probabilities. Okay. A normal distribution, okay, is probably our most common type of distribution for a continuous random variable. Okay. It's symmetrical, but not only symmetrical, okay, it's bell-shaped, right? We have a peak in the middle. It slopes to either side, okay? And instead of having bars, it's a curve. Because really, how wide would each bar be? Well, it'd be infinitely thin, wouldn't it? So this is our normal distribution curve. Okay? And we're going to work with this to find probabilities of continuous random variables, but not of a particular outcome, but of a range of outcomes. I do want to show you the equation for this curve. It's a little intimidating. It looks like this. Okay. It's an exponential, base e, it's e to the negative 1/2 x minus mu, the mean, over sigma, the standard deviation, squared, all over the standard deviation times the square root of 2 pi. You see a normal distribution and the shape of it and its location, okay, the curve depends on the mean and the standard deviation. Now I put this into Desmos here. I didn't use Greek letters. I used M for mean. I used S for standard deviation, okay, just as to use as a slider. And so here's my normal curve right now where the mean is 0 and the standard deviation is 1. Notice what happens if I change the mean. If I slide the mean over to 1, the center of the distribution, that line of symmetry, is now at 1. If I slide it over to 2, it's now at 2. For those of you who've worked in maybe a college algebra or pre-calculus course or even algebra 2, you might recognize x minus m. That minus m moves the graph to the right. Unless, of course, m is negative, then it moves it to the left. It's a transformation. All right, let me put the mean back at 0. Okay. Now, the standard deviation I have set at 1. What happens as I change the standard deviation? The larger the standard deviation, the wider the curve gets, because we know standard deviation describes the spread of a data set. The larger the standard deviation, the more spread out it is. The smaller the standard deviation, okay, the more compact the data set is. Okay. So right now with the mean 0 and the standard deviation at 1, we would call this the standard normal distribution. And from there we can change the mean and we can change the standard deviation, or possibly both, mean, standard deviation. When the mean is 0 and the standard deviation is 1, that's what makes it the standard normal distribution. Okay. The graph looks like this. Notice 0's at the middle, and then we're working to +1 standard deviation, +2, +3, +4, or -1, right? Going to the left 1, left 2, left 3, left 4 standard deviations. Okay. And when we do that, okay, we know the probabilities for each of those intervals. You see between -1 and 1, 1 standard deviation to the left, 1 standard deviation to the right, that contains 68%, okay, as a probability. You see, what's interesting here is the area under the entire standard normal curve is exactly 100%. Interesting thing about it is that standard normal curve actually doesn't end. Okay, it just goes this way forever. It's just the area under it gets smaller and smaller and smaller. It's kind of an interesting concept they're dealing with infinity. Between 2 and -2 standard deviations, that contains 95% of our area under the curve at probability 95%. Between -3 and 3 is 99%, leaving just 1% outside of 3 standard deviations from the mean. Of course, we can use the symmetry to split those in half. The 68's a 34 and a 34. The 95, okay, would make that 13.5 and 13.5 and so on. Again, this is the standard normal distribution. Okay, it aligns with these probabilities. Now, if I move my standard normal distribution maybe to the right and spread it out, those probabilities still remain the same. You just have to figure out how many standard deviations there are away. Now, there is something else I want to show you here with this. And that's where I know the first standard deviation is. There's something called a point of inflection where the concavity of the graph changes. Notice, okay, thinking about like back to maybe parabolas from algebra, opening down, opening up, that kind of concept, that's what concavity is. And I notice the curve right here is opening down in the middle. But if I look over here, it appears to be opening up. The place where that changes is called a point of inflection. It's something that in calculus we actually work to be able to find. There's a lot of calculus that we can do with this equation, but it's complicated and it's not part of this class. So the point where the concavity changes, where it goes from concave down to concave up, is the point of inflection. And to me, if I were to guess based on this graph, it might be right about, I don't know, right about there. Okay. That's a point of inflection. And that point of inflection, okay, comes exactly 1 standard deviation away from the mean. So if the mean is 0, that's 1. Okay? Or if this is mu, this is mu plus 1 standard deviation. And the same thing's on the other side. So going straight across, there's another point of inflection. This is where the mean minus 1 standard deviation is. And I can use that, the fact that this distance then is 1 standard deviation, to approximate where my second standard deviation would be. That'd be what, maybe about there. So this is mu plus 2 standard deviations. And then I can go about that same distance out here. This is about where mu plus 3 standard deviations is. And I know it's not perfect. Let me just fill in the other side. See, that's about mu minus 2. If I do that again, out here is about mu minus 3 standard deviations. I know it's not perfect, okay, but that's kind of a helpful thing as you're sketching out your normal distribution curves, is to find that spot where the curve switches, okay, point of inflection, and use that as the mean plus 1 standard deviation. All right, just looking at the timing, I've got a bell that's about to ring here. So I'm going to wrap up this video now, and I'll complete it in a second part to this video.